Hello, good evening, everyone.
Good evening, sir.
Hi, hi all. So today we'll be discussing the summary for week 10. We'll be doing the summary here and we'll start with it now. I'll just share my screen. I hope I'm audible to everyone.
Yes, ma'am, you are audible. Yes.
So,
But ma'am, your screen is not showing.
Sorry, ma'am, I joined just now. Ma'am, what we will discussing today?
we're discussing week 10 summary. We're doing the week 10 summary. Just share my screen in a minute.
Okay, ma'am.
Is my screen visible?
Yes, ma'am.
Yes, ma'am.
Okay, so the beginning of graph theory we discussed in the last session, just the beginning of it. What's a graph, and then just one application of it, which was the graph coloring. We discussed this in last session, and after this we'll discuss the second
Ma'am,
application.
in the last session, I joined till 9:30, but till then you are discussing week 9.
Yeah, it's towards the very end I discussed, like for the last 20 minutes or something, I guess I discussed the graph theory.
Ma'am, can you
We
please
can
discuss that again?
basics it, because it's a long thing, so if I'll discuss that again here, it would we won't be able to finish the whole thing today.
Ma'am, just summary.
We just discuss what graphs are. So this is what you represent a graph with. Basically, the graph is basically vertices. So V is the connection of, this is a set, this is also a set. So V is the connection of these dots that you see, these are called vertices, and then these are called edges, right? And then the collection, this is a set, which is the collection of all the vertices here. Like, let me just call this V1, V2, and V3, V4. So this is the collection of all V1. So the set of vertices is V1, V2, V3, V4, and edges here are V1, V4. So this is so in this case, it's V1, V4, V4, V3, and V1, V2. These are edges. That's one thing that we did. And then we just did one application of it, which was graph coloring. So in graph coloring, what we do is, basically, it's like when you have, let's say, let's just say you have this graph. So what you do here is that you just make sure that no two adjacent vertices, adjacent means these two vertices that are connected by an edge. This is an edge, right? So the two that are connected with an edge are called adjacent vertices. So no two vertices should have the same color. So we'll assign, let's just say we're assigning this with color green. So we can't assign green color to this one. We can't assign green to this one and not to this. We can assign the green to this one. And then we'll have to assign a different color to this one, let's say red. So you can't assign red and green to this because this is adjacent to both these two vertices. So you have to assign it. And similarly, you can assign either red or blue because you already have two colors, so no need to take another color. Let's just assign either blue or red. You can assign either of these two colors. So the minimum number of colors that you need to give to these vertices such that no two adjacent vertices are same is 3. So where what is the application, and then we discuss the application of this. That you can check from the server. So what's a vertex cover? Vertex cover is basically it's a subset of vertices. So basically, let's just call this set S, and it's a subset of the set of vertices where you collect all the vertices such that each edge has, so if you have all these edges, you need at least one of the vertices from each edge to be in this set. That's your vertex cover. So if you want to find the vertex cover for, say, this graph, what you do is you start from this, say, this edge, then you need at least one vertex here. So let's just say we chose B5. Then from this edge, you need another vertex. So only one is required. You don't need to put both of them. So this will be, let's just choose B2. And then from here, this edge, you already have V2, so you don't need to take V3. But from this edge, you don't have V1. No, neither have V1 nor have V3. So let's just choose one of them, V3. And then from this edge, you already have V2. So you don't. So this is the vertex cover. This is vertex cover it doesn't have to be unique. It can be something else too. This could also be the vertex cover. You can choose V1 instead. And then so these two edges are covered. And then this third edge is also covered. And then you can pick this edge and this edge. So from here you can take V2. So this is your V2. So actually, this one should be the one here because this one's a longer one. So it's like the minimal set that you need so that every edge is covered, so that you have a vertex in every edge. Is that okay? Is this fine with everyone?
Ma'am. A vertex in every edge, is it? I mean, I didn't get that.
So you look at all the vertices and you need the minimum set such that every edge has at least one vertex, and not at least, it has to have one vertex, only one. So it's, if you have this edge, you have a vertex V1. From this edge, you have a vertex V1. From this edge, you have a vertex V1. And then from these two edges, you have a vertex V2. So this covers everything. It's like if you have, say, there's one popular example of this for the security cameras. So let's just say that these are the corridors of some building and you have security cameras installed here. So you just need to install two security cameras, one here. It'll take care of this and this corridor. And then one security camera here, which will take care of this and this corridor. Is that fine?
Okay.
And then you don't need one here. You don't need one here.
So
that's the application of this.
We don't need one between V1 and V2, right?
Yes. Sorry, what?
We don't need a vertex. We don't need a edge between V1 and V2, right? Here.
Yeah. Even if this edge is not here, it still works.
Okay.
It still works. Okay. This is your vertex cover thing. And then,
Excuse me, ma'am.
yes.
Ma'am, I've sent a question in the chat. I have a doubt in it. It's from extractivity one of Leap.
We're discussing the summary right now, and it's a long thing, so I don't think we can take up the doubts for now. Let's just get done with something, and then
Okay,
probably
ma'am.
we'll be able to take the doubts. The third application here is your independent sets. And for the independent sets, what you do is, let's just say you have a graph. What you make sure is that, so if you pick this vertex, I'm just telling you how you find an independent set. Instead of just defining it, I'll just tell you how you find an independent set. So if this is a vertex, let's just say, then you can't take this vertex because it's directly connected to this one. You can't take this one, and you take the other one. So you can take this vertex, V2, and you can't take this thing either. So let's just say this is this thing. So
Excuse
this
me,
is
ma'am.
an independent set, and if you, yes,
Ma'am, please explain independent set. My network was a bit low.
okay. Independent sets are basically such that these two, okay, so when you have vertices and you have an edge between two vertices, means that they are these two are somehow related. This is the relation, this is some relation that you're defining, right? These two are connected to each other. So what we want is independent sets means that you would want a set which with vertices that are not related to each other. So V1 and V2 are not related to each other. So it's an independent set. Similarly, if you start with V5, you'll have V5 and then all three are connected to it. So it's V5 and V3. V5 and V3 are not connected to each other. So V5, V3 would be an independent set.
These are not sets of vertices, right? These are sets of edges.
No, these are sets of vertices.
Okay.
This is a subset of V.
Ma'am,
So-
here by V5 and V3, you mean that V5 and V3 have edge means relation?
Yes, this means they are related to there. You must have defined some relation here, right? The edges are relations only between the vertices.
It should be direct or indirect in independent set because as you create V5, V3 contain in V.
We don't need a direct indirect thing here. Independent sets do not need the direct and indirect stuff. We're not getting into that. It is applicable in both kind of graphs.
Okay.
Then for the V1 part, you can have V5. You have V5, V4, and V3 connected to, so you can only have V2 here. These are independent sets. If you need to find them in maximal independent set, and then we have something called maximal independent set. So as the name suggests, it's a set of, it's obviously a subset of vertices, the collection of vertices only, but how do we find out this maximal independent set? We want to find a set which is the maximum. These are two elements. We want to find something which has maximal number of elements, right? So we just start off with a vertex, which is, see, if you pick this one, we know that it's connected to a lot of other vertices. So let's just start with something which is not connected to a lot of vertices. Because you ultimately what you put here is something which is not connected to this the vertex which is already there. So if V2 is here, you need something which is not directly connected, which does not have an edge from V2 to that vertex, right? That's the vertex that you put here in this set if V2 is already there. So let's just start with V2 because V2 is only connected to one of them. If you want to have maximal number of elements in this set, you should start with something which is connected to least number of vertices. Is that clear? So you start with V1, sorry, V2. Don't start with these, at least not these two, because they are connected to literally almost everything. So either start with V2 or start with V3, and then you can put V1 here. But in this case, what happens is you're getting the same. So you're getting two elements each. Even if you start from V2, you'll get a V1, and then you can't put any other thing here. Let's just say if you had something else here too. Let's just say you have V6 here, and then a V7 here. If we extend this thing, then don't start from this vertex, instead you can start from V2, and then you can put a V1, you can't put V5, V4, can put V1 here, then can't put V3, can put V7 here. This will be the maximal independence. Is that okay?
Ma'am, why not V3?
Because V3, if you start with V2, and if you want to put V3 here, then you can't put V1 because they are connected to each other by an edge. So if you're putting V1, just put V1 and then you can put V7. This also works. The maximal independent set is not something unique, but the number of elements probably would be unique.
But we
And
could
you
have
would be
also
given
had
something-
V2, V3, and V4. No?
What?
We could have also had V2, V3, and V4, right? They're independent as long as they're not shared.
They're not if they're not sharing an edge, then they're independent.
Okay.
V2 is here, V3 is here, and V4 is here. Yeah, that's fine too. This is fine too. So what's
Ma'am,
the
can you take
application of
one
this?
more example?
Of the graph, or do you want a practical example? Because we're doing a practical example now.
Ma'am, anything you can. Because it is a bit confusing for me.
Do an application and then you will see how we use it. So let's just say that you have classes to attend, or let's say workshops to attend, and your classes are like, say this is the first class, the second class, third class, and fourth class. So let's say it's from 9 to 10, and then this is from 9:30 to 10:30. And then this is from 10:30 to 11:30. And then this is 11:30 to 12:30. So if you have these classes, what you do is you start off with knowledge and the edges. So we're defining the vertices to be the classes. So first class, this is vertex 1, second class, third class, and fourth class. And then you have, so there is an edge if they overlap. Like this one, these two classes overlap with each other, right? So they have an edge.
Ma'am, but not completely overlap now. It's 9 to
We define this thing. The edges is, we define the relation which will define the edges. So we are defining it to be an edge. So there is an edge, we are defining it this way.
Sorry, ma'am.
We get to define the edges. So I am defining the edge to be in this manner. Once you let me complete, you know why we're defining the edges in this manner. Let's just take something more overlapping here. Let's just take 10, 15 here. And let's take another class from 9:15 to 12. So first, and see, there's no rule to, you need to understand this. So this is an application. So if you want to use the graph to solve this problem, the problem is, let me just define what the problem is and why do we need the graph here. We want to find the maximum number of classes you can attend here. So it's very simple. If two classes overlap with each other, even if not completely, you can't attend them, right? So you can't attend this and this class together. Even if they don't completely overlap each other, but they're still overlapping in some part, right?
Yes, ma'am.
That's why we have an edge here. Because we want to find, let's say I am attending some classes, so I can, if I'm attending this one, I can't attend this
So, ma'am,
And I can-
overlapping means having an edge.
Overlapping means nothing. In this particular example, we're using the edge as something which this edge represents. Whenever you have a graph, the edge represents something, right? It represents a relation between these two vertices. And the vertices here are classes. This is class 1 and this is class 2. So it represents a relation. What's the relation here? The relation is, if these two classes overlap, then I consider it to be related. These two classes to be related. These two classes don't overlap, so they're not related to each other. Is that fine? Let me just define the problem for you first. So these are the classes that are scheduled, and you have to attend the maximum number of classes from here. So how do you solve this problem? What do you think you should be doing? So if we don't use the graph, what we'll do is we'll take this class and then we'll skip this one. In this one, it's pretty clear because it's not a very complicated thing here. So we'll attend this one and then we'll skip this one, and we can attend this one and we can attend this one later, and we can't attend this one because it overlaps with this one. So we can attend three classes maximum, right?
Yes,
Even if
ma'am.
even if you choose any other class, let's say you want to attend this one, then you can't attend any of the other ones because it's okay. If you start with the second one, then you can choose. You can't choose the first one, can't choose the fifth one. You can choose, and you can't choose the third one either. So you can choose the fourth one. So only these two classes then you will be able to attend. So that's what we are doing with the help of a graph. This is a very small data, and a lot of things are not overlapping with each other. That's why it looks easier. But when you'll have a lot of complicated things, you won't be able to do it without a graph. That's why we need a graph. And how do we use the graph here? We put an edge here. So let's just say there's an edge between 1 and 2. If these two classes coincide or if they overlap at all with each other, even if it's for 15 minutes. And we don't have an edge if the classes are like completely disjoint, like this one. This is from 9 to 10, this is from 10:15 to 11:30. So 1 and 2 they have an edge, then 1 and 3, they're not overlapping, so 1 and 3 do not have an edge, then 1 and 4 do not have an edge, 1 and 5 have an edge too. And then these two classes are overlapping, so second and third, they do have an edge. And third, fourth, they're not overlapping. And third and fifth are overlapping. Fifth is overlapping with literally everything. So it's overlapping with all. This is the graph, right? Now what you do is you need to find the maximum number of classes that you can attend if you want to. So if you start from, so I just said how to, so we'll use the maximal independent set here. And how do we use this maximal independent set here? So as we discussed, we start with the vertex, which is connected to the least number of vertices. So this is connected to the least number of vertices. Let's just start from this one. And then you can have this one. And then you can have this one too, and this one too. Is that okay? So these are the classes that you can attend. The maximal independent set will be V1, V2, V4, and V3. Is this clear to everyone?
Yes,
Ma'am,
Yes, ma'am.
with
V2
the
and
graph,
V3 are not, they are connected, right?
So then we don't consider them to be connected because they're not connected by an edge. Although they are connected, this is a path. So what's the difference
No,
between,
ma'am,
I'll just
V2
write
and
it here.
V3.
Between V2 and V3. And unlike the previous
V2 and
example,
V3, yeah, this is
unlike the previous example,
okay.
here there is a lot of connection. So, but I got it. I mean, what you're saying.
Okay, we had 10:30 previously here, right? Then it's not connected. Then let's just take 10:30 here. We had 10:30 previously here. Is it fine now? Wait, then no, they are 10:15 was fine, right? What was wrong?
I'm only looking at the graph.
Okay.
So,
Yeah, let's not. V2 you can't select, so it's 2 you can't take. Okay. Is it fine now? But if there was no edge here, then still you couldn't attend this one, no? Because it's coinciding. This is overlapping with the first class.
ma'am, if we are trying to find the maximum number of classes that we can attend, then and we chose 4 and we started with 4, we ended with all these 3 dots. Do we need to choose another point and do the same exercise to make sure that it's maximum, or it will be always maximum?
Well, that's the ideal approach. But when you know, see, if you choose this one, this is literally connected to everything. So if you start with this one, you'll end up with only this one. There's no point. So you can try it, but it's usually with the one which has least number of connections. Usually it works out. Otherwise, you can try with the other ones. Let's say this has 2 connections, so you can test this one, or this has 2 connections, you can test this one. this and this are not going to be the cases.
Yes, ma'am.
I can
Thank you.
safely assume that this you can start from the one that has least number of connections. And by connections here, I mean that the least number of edges. Okay. Then we have the other application, which is matching. And then with it, we have these two are not the same terms. They're related, but they're not same. And then we have perfect matching. So for a matching, what you do is, so this is basically the collection of vertices, not vertices actually. It's the edges. It's collection of the edges that are disjoint to each other. So you collect edges that are disjoint to each other. If you define it, it's basically a set M, which is a subset of E. E is the collection of edges. So it's a subset of edges. So it will have edges. Edges we denote by this thing. So if V1 and V4 has an edge, and if it's undirected, you can do V1, V4 or V4, V1, doesn't matter. Otherwise, if it's directed, okay, we'll come to the directed part later. We don't need it here. So this is what you represent an edge with. Or E is the collection of all the possible edges in the graph, and M is a subset of it. So what kind of subset is a matching? It's a subset where only those edges are involved which are mutually disjoint. So this mutually disjoint means that let's just say they don't have a common point. So V1, V4, and then you can have V3 and V5. These two are mutually disjoint, or you can say disjoint because they don't have a common point, right? So that's what you want here. This is called the perfect matching set. So let's just see an example where we use it. Let's say you have a project going on,
Excuse me, ma'am.
and yes,
Can you explain perfect matching?
yeah, we'll discuss it once we define what matching is.
Okay.
Okay. So let's just say you have to pair up for project. Let's just say you guys have been assigned a project and you have to do it in 2 pairs, or you can do it alone too, but you're allowed to do it in a pair. So let's just say that we're only taking a few number of students. So let's just say this thing is there. And this is the graph, and I'll tell you how so whenever we have this I want you to be clear with, that when you have, there are two things. One are vertices that are like the things that are there, and then how are those things related to each other? That's this edge. Edge is basically what are you defining the relation to be. I hope you understand what a relation is. We've done it before, and so if there's a relation between them, then there is an edge, and you define that relation according to the question. Like we defined in the previous example, that's how you define the relation between edges. So here, the relation we're taking is, let's just say that, so everything mostly is given in the question. Let's just say that you, V1 and, so if this is the graph, let's just say V1 and V6 are friends. So we're assuming that the pairing is going to be according to the friendships in the group. So if you are friends with someone, then you're going to pair up with them. And if you're not a friend with them, you're not going to pair up with them. So if you, let's just say V1 is friends with V3, it's friends with V6. I just denote the friendships here. So if you are friends, so this person has 2 friends now, so he can pick one part, right? And one of these 2. So similar is the case with everyone else. So how do you find a matching? So a matching could be, in this graph, it could be V1 and V6. So this is done. Then you can take V2 and V3. This is a matching.
Why not V1 and V3?
You can take V1 and V3 too. That's also a matching. Matching is not something unique. You can take V1, V3. And then you can take
V2, V5?
You just need to make sure that this subset of edges is, the edges here should be disjoint. That's all. Everything that has disjoint edges is going to be a matching. That's how we defined it, right? So we can't list all the matchings here. It will take a lot of time. I just want to give you, whenever I say that this is a matching, there are other matchings too. Doesn't mean it's a unique thing. Is that okay? Obviously, V1, V3 can be paired together, then V2, V6 can be paired together. Or V5, V2 could be paired together in this one. And let's just try to find a perfect matching here. So what's a perfect matching? Perfect matching is when, so is matching clear to everyone?
Yes, ma'am.
Okay. So perfect matching is when you have, so it's a matching plus you make sure that no vertex is left out. These are two conditions. So obviously every perfect matching is a matching. And not the other way around. Every matching is not a perfect matching. This is not a perfect matching because V6 is, which one's left out? V5 is left out. And then let's just try to find a perfect matching. Can we have a perfect matching here? If we'll take V1, V6, we can't take. So let's just take V1, V3. And so V5 has only one connection. So V5 must be paired to V2. And then V3 and V1. Have we missed a vertex? V4 is not here.
Be even numbers, no, ma'am? The number of vertices.
It has to be even. Number of vertices to find a perfect matching, you'll have to have even number of vertices. Otherwise, so this one we missed the V4 part here. That's why we couldn't find a perfect matching. Now you can just pair it to this one. I hope this works out. So if you have this thing, V5 is paired to V2, say, and then so V4 has only one connection. So let's just match V4 to V5. I hope you understand why V4 needs to be matched with V5. It cannot match with anyone else. This has to be in this perfect matching set. V4, V5 has to be an edge there. Then V2 can be matched to V3. That's the only choice left with V2. No, V6 is also a choice. That's all right. And then V1 and V6 can pair up. So this can be this is a perfect matching. Again, this is not something unique. It depends on the graph. It can be unique, but it doesn't have to be. Perfect matching, if it's unique or if it's not unique, depends entirely on the graph.
Now, while V5 and V4 is not a perfect match.
Which one?
Why V5 and V4 is not a perfect match?
V5 and V4 is here. It's, see.
Why it is not a perfect match?
This entire set is a perfect match, not a particular edge. This whole thing is a perfect match and a match. Both of them are subsets of edges. We've defined it now. It's a subset of edge. Perfect match is also a subset of edge. Edge means a collection of all the edges.
So, ma'am,
this whole thing is a perfect match.
Doesn't have necessary to include all
can
the
you
edges.
tell me when will be a it is a perfect match?
Ma'am, if V2 and V3 are perfect match, then V2 and V6 is also perfect match.
Perfect match is not an edge. It's a collection of edges where you collect all the edges such that it's a. Do you understand what a matching is? Because otherwise you can't understand what perfect matching is.
Ma'am, can you please tell me what is mean by perfect match again? Once again.
First, you need to know what a match is. I don't think you understand that part either. So a match is when you need edges. It's a collection of edges such that no two edges overlap with each other. So if you have V1, V6 here, the other edge should not have V1 or V6. Like this does not have a V1 and V6. Okay, that's a matching. So this whole set is a matching. Why are we calling it a matching? Because these two decided to pair up, and then V2 and V3 decided to pair up. And maybe these two, we don't know what these two are doing. Maybe they're not pairing up and whatever it is. So this is a matching. So this whole set is a matching. We don't say V2, V3 is a matching, V1, V6. This whole set is a matching. Is that all right?
Yes, in a set, all the elements should match each other. Because one element should not be in the another one, and another one should not be in another one, like that.
Yes, correct. So this Matching
So the
is,
elements in matching should be disjoint, right?
yeah, in a matching is a set. Let me just write it here. In fact, it's a subset of a set of edges.
Matching necessary not include all the edges, right?
No, it
Then,
can't
ma'am,
include
over
all
here,
the edges,
P6
right?
and P2 is not disjoint. So why are we calling it matching?
B2 and B6.
Yeah, they have an edge. So it's not disjoint.
But okay, you're getting the this thing wrong, I think. We mean by disjoint, we mean this thing. So you have B1, B6, let's say, then B6 and V2. These two are not disjoint because they have a common vertex here. So by disjoint here, we mean that they should not have a common vertex. That's what we mean. Is that okay?
Okay, okay.
So these two do not have a common vertex. That's why it's a matching. Matching is like we've discussed, you can partner up with this, you can just look at partnering up for a project. Pairing
Ma'am,
up
in
for a
this
project.
matching set, can we add a V4, V5 too?
Yes, because matching, yes, you can. You just need to check that the edges should be, this is an edge, it should be disjoint with all of these two edges. So V4 and V5 is nowhere. So it's fine.
Yes, ma'am.
And then we have a the perfect matching. So perfect matching is a matching such that every vertex is covered. So you should make sure that no vertex is left out. It's like everyone should be in a pair with someone else. It's like everyone has a partner to do the project.
Ma'am, in this perfect matching set, can we say that if there are odd number of vertex, then we can say it doesn't have any perfect matching?
Yes, because if you have odd number of vertices, obviously one is going to be left out, right? No matter what your
Yes, ma'am.
graph is, one will be left out. You can't have all of them covered.
Then can we say that it does every odd number of vertex doesn't have a perfect matching
graph
set?
with, yes, you can say that if there's a graph with odd number of vertices, then it does not have a perfect matching.
Yes, ma'am.
Okay, the perfect matching in the application part is clear for this, right?
What is the use of this matching set?
We just discussed we started with the application part only, that you're doing a project. Let's just say you're doing a project and these are the 6 students that are supposed to do a project and they can pair up. So either they can pair up or they can do it on their own without pairing up with anyone else. So this is like V1 and V6 are pairing together to do the project. V2 and V3 are pairing up to do a project. So since you can only pair up with one person and you're only supposed to do one project, so you can't have a V1 and V2 here, right? That's not even an edge. And these are the friendships here. So let me just write down the assumptions here. We're assuming that
this means that one vertex should connect with another vertex with any given edge.
Yes. So it basically the vertices here are students and the edges here are if they are friends or not. So V1 and V2 are not friends. That's why there's not an edge here. So if they're assuming, this is an assumption that if they're not friends, they're not going to pair up for the project. This is an assumption. Okay. So if you have to decide who will be pairing up or what can be a pairing. So these two can pair up together. These two can pair up together because they're friends. And then these two can decide if they want to pair up or not. Right? So this is a matching, and a perfect matching would be when every student has a partner to do the project with. Is that okay?
Ma'am, same example, can you draw with the odd number of vertices, the friends example?
We
and
did
then
it
can
with
we
the odd number of vertices. When we did not have V4 here, V5 was left
Okay.
out here. Because
Okay.
V5 do not have anyone to pair up with. Is that
Ma'am,
okay?
in perfect matching, no edge gets left out, right?
Yes, no vertex should be left. So it should
And
be
so they
paired up
should
with
be
some.
even. But ma'am, then
Not
if V4 was not there, we could make V5 and V2 as a pair.
If you will
In
make
absence
V5 and
of
V2,
V4.
let's just say V4 is not there. You will pair up V5 with V2. Then V2 cannot pair up with V3. So V3 will be left out.
Oh, okay,
You'll
okay,
pair up
got it.
B3 with
Okay, so
B1,
have to
then
be
B6 will
even
be,
edges, right?
yes. One of them will be left out if there are 5 number of vertices.
Ma'am, another small doubt, ma'am. If you are
Yes.
just considering we have even number of vertex, one is connected with, we are just calculating, we are just doing the matching set. At the end of the thing, we have 2 vertex remaining, but there is no common edge between the both vertex. Can we add them both?
No, you
In that,
can't. That means because we just discussed the assumption here, right? We discussed if they're not friends, then they're not going to pair up for the project. So if V1 and V2 do not have an edge, they cannot pair up for the project.
ma'am, yes, ma'am,
That will be given in the question.
As ma'am, another doubt, ma'am, in this case, as you given drawing, it's easy to find out the number of vertex and the connection points, so you can easily calculate. We can find out the perfect matching set. What if there are a huge number? There are a huge number of vertex and huge number of edges. If there are such type of thing, means how we can calculate that?
You won't be given a lot of edges where you can't find a perfect matching. If there's a question on perfect matching, you will be given a number of vertices from where you can figure out which one should be paired together to make a perfect match. Is that
It
okay?
will be less countable only now, right, ma'am?
Sorry?
Ma'am, in the question there will be less countable, like 5, 7, like that only,
Yeah,
na?
only that much. You're not going to get a large number of vertices there.
Yes,
Okay.
ma'am.
Then we have adjacent matrices. So what's an adjacent matrix? So when you have a graph thing, we know graph is basically collection of vertices and edges, right? Together. So this is a graph. Let's just say this is a graph. And then you need to make a, so what does adjacent matrix do? We mention all the, let's just simply write 1, 2, 3. And then do a 1, 2, 3, 4, 5 here. Before discussing the adjacent matrix, let's just discuss directed and undirected graphs. It's a pretty simple concept. So directed graphs are where you have directions. So far, we've been doing only undirected ones. And then there are undirected graphs. Undirected graphs, we've discussed the cases. And then it's like in the friendship case, it would likely be a undirected graph, right? So if this is a friend of this person, this is also a friend of this person. In other cases, then there are directions where, let's just say you're, so an example of I'm just giving directly the example. Directed graph means you have directions here. So in this case, what you mean is V1 and V2 are connected. So V1 is connected to V2, V2 is connected to V1 by an edge. But when we have directions here, let's just say we have this thing and we have directions with all the other, I'm not drawing it. Let's just draw it here. Let's just say you have these vertices. So this is a directed graph where there is a direction for everything. So it's like you can just take it as who's the, if there is like, let's just say that these are places or destinations and these are the routes. So if you have a route from here to here, if you have a route from here to here, then if there's no edge here, this means that's how we're defining the edge. Don't be confused by how do we define it. It will mostly be given to you in the graph. And what does the edge mean here? The relation is given almost all the time in the graphs. So if we point this thing, that means that this destination and this destination does have a path from here to here, but it has a path from, so it's, you can't take a path because paths are usually 2 ways, right? So let's just say that it's let's just say that this is a task thing that well, let's just not go there. Let's just take the simple example of aeroplanes and airports, or all of these things. So let's just say that these are airports. This is an airport. These vertices are airports, and then this is if there is a flight from here, this airport to this airport or not. This means that there is a flight from this to this airport, and this means, so this and this are not directly connected. This means that this and this does not have a direct flight. So you don't have a direct flight from this airport to this airport, but you have a you have a flight from here to here, and then you can go from here to here. Is this clear with everyone? This is one example of directed graph. And then undirected graphs have done a lot. The friendship one was an undirected graph. So I hope the directed graphs and undirected graph part is clear to everyone.
Ma'am, can you tell me, is there any relation between maximum independent set and minimum vertex cover?
The minimum vertex cover is basically the minimum number of vertices that you need to cover everything. And then pairing, the other one you're asking is independence, right? So they usually do not have a direct relation, not a very explicit relation, which is clearly visible. So there's not really a relation. Though graph coloring thing and independent sets you can have, I don't want to go into that detail, but graph coloring and independent sets do have a relation. So if you have an independent set, then you can color it with the same color. Like let's just say that let's just say you have this thing. So if this and this thing are independent, then you can color with this is an independent set, and that's essentially the maximal independent. So you can color it with the same thing, right? Green, no problem.
What makes this? What you are then? Why you are just telling this as a matrix?
It's okay. We come to the matrix in a while. Is this thing clear? Someone asked a doubt. So graph coloring and independent sets are kind of related to each other, but independent set thing and the other thing that you asked is they're not related to each other really.
Okay, ma'am.
Then in the adjacent matrices, so if this is an undirected graph, so for an undirected graph, what you do is you just see if there is an edge or not, and then you put a 1 here if there is an edge. So this is, let's just say if there's an edge from, so this is not considered. We always consider, okay, V1 and V1 does not have an edge. So we don't consider we don't consider an edge to be there from V1 to V1. So there's a 0 here. And similarly, there's no from 2 to 2, no from 3 to 3, and 4 to 4, and 5. This is what we consider. There's no.
Ma'am, I have a doubt in this case.
Yes.
Ma'am, in this V1, we are just drawing edge to V1 to V1 is possible, right?
It is possible, but that's not in your syllabus right now, not for the week 10 at least. So if you could have something if it was a self loop, and self loops are not in the syllabus, so let's just not do there. So there's a 0 here, everywhere. Is that okay?
Yes, ma'am.
Okay. And then there is an edge from V1 to V2, so you can put a 1 here. So wherever you see an edge between two vertices, there's a 1. So 1 and 2 has an edge, so it's a 1 here. Then V1 and V3 has an edge, so it's a 1 here. So I hope you can complete that. We don't have enough time because there are a lot to discuss. So this is a matrix.
So two vertices has two edges.
Sorry, what?
If two vertex has two edges, like V1 connects to V3 and another edge also connects V1 to V3 directly.
Yeah, so so in this row, and in fact in the column too, because it's an undirected graph, right? So in this row, you're going to have only 2 entries, 2 non-zero entries. And here you have a 0, 0. And here too. For an undirected graph, you'll have 1, 1 here, and then a 0, 0. Is that okay? So
no,
for an
I'm
adjacent
asking
matrix.
Ma'am, my doubt is V1 to V3, we have V1 to V2 and V1 to V3, we have only one edges, so we are considering as 1. What if we are having two edges, like V1, there are two edges connecting V1 and V3, V1 and V3.
You cannot have two edges, and you will not be given two edges anywhere. So if there are two vertices, there's only one edge between them. But an edge means that they're related to each other by some relation. Why would you put two edges there?
Like as you said, a direct.
So in a direct graph, you have.
Path.
Okay, we'll talk about direct now.
For like if as a flight
this part
train.
Is clear. So for the.
Yes, ma'am. For a flight.
We'll do the direct part
from V1
in a while. Okay, give me a minute. I just want to make sure that the undirected graph part is clear. This matrix is clear. And then we'll do for the directed part. So if you have a directed graph, let's just say you have this graph. if you have this thing, then how you draw it is to write 1, 2, 3, 4 here, and a 1, 2, 3, 4 here, and then this is so this is the incoming. So if there is a edge from 1 to 1, so this is again 0, 0. We don't consider an edge to be from 1 to 1. So the diagonal is always 0 in adjacent matrices. And then if you have an edge from V1 to V2, you put a 1 here, V1 to V2. And this would mean there is an edge from V2 to V1. So there's no edge from V2 to V1, so you'll put a 0 here. And similarly, you fill the entire matrix. Is that okay?
Yes, ma'am.
No, I can't understand.
In an undirected graph, what you do is there's a difference between. So undirected graph is, have you heard of symmetric matrices? So this is a symmetric matrix, is this one, because this entry is same, then this entry, this one. So Aij is the same as AjI. So in adjacent matrix for an undirected graph, you have Aij the same as AjI. This is a feature of adjacent matrices for undirected graphs. But that's not the same with directed things. So what happens there is, if you have an edge from V1 to V2, this means you have an edge from V1 to V2. And this means you have an edge from V2 to V1. So if you have an edge from V1 to V2, then you have an edge from V2 to V1 as well, because it's undirected, right? You don't have directions here. So if there's a 1 here, it will be a 1 here as well. There's a 1 at A, let's just say this is matrix M. So if you have a 1 at M13, you'll have a 1 at M31 as well. Is this part fine?
Ma'am, if we are saying like V2 to V1, so V2 here is considered in the row and V1 is then considered in the column. Is it?
Yes. Okay. In this case, see, in an undirected graph, you can be a little careless because it doesn't matter. There's no direction, right? But here you have to be careful. If there's V1 here, this means V1 to V2. So if you'll put a 1 here. This means V1 to V2. Is that okay? And this part is 0 because you don't have an edge from V2 to V1.
Yes, ma'am.
So whoever had a doubt in this thing, is it fine now?
Yes, ma'am.
Okay.
Yes, ma'am. Now I got it.
Then you have something called degree of vertices. So when we discuss about, let's just say we're discussing undirected graphs, so you only talk about degree. And when you have directed graphs, you have two things. One is the in degree of a vertex. This is the vertex. And the other one is the out degree. So as in this one, let's say, so the degree of V2 is the number of edges that are that have V1, V2 on it. So there are two edges that have V2 on it. So the degree of V2 here is 2 and the degree of V1 here is 2 as well, right? So the degree of V2 is 2 here. But or let's just consider this graph without directions. So if we forget the directions for a while in this graph, in this one, then the degree of V1 is, let's just take degree of V2. Degree of V2 is, if you forget the directions, the degree of V2 is 3, right?
3.
Let's just take V2 everywhere. And the in degree is the number of incoming edges. Incoming means this. If the edge is coming towards it, then it's an incoming edge. Otherwise, it's an outgoing edge. So the in degree would be number of incoming edges. So there are two number of incoming edges and one number of outgoing edge. This one. Is this fine?
Yes, ma'am.
Yes, ma'am.
Okay. Then we have the question of reachability. Reachability means if you have a graph, let's say this is the graph, then which vertex can you reach from where? Let's just say this is the graph. So if you start from, and this is generally in the directed cases. So let's just draw the directions too. So this is it. So we need to, let's just make a clear diagram. V3, V4. So if you have this thing, reachability means which vertices can you reach? Okay. So there's one thing called edge, and then there's a path. So edge is when you have edges this thing. So if V1 and V2 are directly connected, they're connected by an edge, which is this edge, right? V1, V2. That's how you denote it. And then the path is this is a path, V1 to V2, and then V2 to V3, and then V3 to V5. Then you can come back to V2 again. So this is the path. Is that okay? That's the difference between an edge and a path. And then reachability question is which edges? Yes.
Ma'am, understood the reachability. Can you please tell which kind of question is asked on reachability? Do the number of paths for reaching or anything else?
Kind of questions asked is which vertexes. Okay, so reachability is basically which vertices can you reach from, let's say, V1, right? So that's reachability problem. And then you have ways to do reachability. And basically you won't be asked the number of paths that you can reach this vertex. You won't be asked those things, if that's the question. You won't be asked the number of paths that you can choose to reach from some point to some other point. It's basically which points can you reach, and then you'll be asked to find out ways to go there. We'll come to that point in a while.
Ma'am, reachability can be both directed and undirected.
So reachability, it's basically, in most of the cases, it's in directed graphs only. But if you want to talk about reachability, in undirected graphs, it's what do you talk about there? Because if you don't have directions, maybe you can talk about them in undirected graphs too. So if there's a question based on that, you can talk about it. I think you can. You can talk about reachability from there too. Let's just say you have a friend circle, and then if there were no directions here, you can say that these are friends. The edges are friendships here. So you can just say that can this person connect to this person? That could be a thing. Yes, that can also be a thing.
Okay.
Let's just say you have to ask for help, that this person wants to ask for help. So can this person ask for help from this person? Or is that okay?
Yes,
Ma'am, we can't obviously, but they can through this person.
Ma'am, if we considering as a directed means we for few edges we can't, for few vertex we can't find the reachability, right?
Reachability, see, if you obviously if you have this thing, so there could be, so you can't reach this. I don't think. Okay, if let's just reverse the direction of this one. If you have an edge from here to here, then you can't reach from V1 to V5 because you can't go here. You can't follow this path, can't follow this path. Then you can't follow this one either. So you can't reach from V1 to V5. So obviously there are cases when you can't reach from one vertex to the other one. That's why we're discussing reachability, to see which vertices can you reach from V1. So can you reach V2? You can reach V2 obviously, can reach V3, you can reach V4 too, but you can't reach V5. Is that okay?
Yes, ma'am.
Okay.
Ma'am, I have one doubt. Reachability from V1 to another vertex means we can connect another two or more edges. Like it's not necessary. It should be directly connected.
That's what we are talking about. They don't need to be. If you're talking about reachability, okay, let's just define reachability here. Reachability means if you can reach from V1 to V4, obviously not directly. You can't reach from V1 to V4 directly, but there are edges here, so there's a path. So reachability means V1 or V4 can be reached. Let's just write it here. Vi can be reached from Vj. If there's an edge, if there is a path, that's how you define it. Path from Vj to Vi. The direction is important. You need a path from Vj to Vi. because you want to reach from Bj to Bi. So there should be a path from Bj to Bi. Like in this case, you need a path from V1 to V4. So there is a path from V1 to V4. So V4 is reachable from V1, but V1 is not reachable from V4.
Okay, ma'am.
Is it fine?
Got it.
Okay. Then we forgot to mention one thing, which is adjacent list, adjacency list. Adjacency list is we can make the list from this graph only. So adjacency list is basically you write the vertices here like V1, and then you write the vertices that you can reach from V1. So V1 in this list, for V1 you will have V2 only. So you can only reach V2, so there's only V2. Similarly, you make the sets for other vertices too. So from V2 you can reach V3, you can reach V4. That's it. That's the same with every other vertex. This is fine. Adjacency list.
Ma'am, I have doubt in the graded assignment of week 10. Can I share?
The assignment can't be discussed right now because its deadline is not yet passed. So we can't discuss that here.
And what about the V5?
So can you just explain the similar concept from another question because it is not clear? Means if I show you the question, can you explain the concept, not exactly the question?
If it's a conceptual thing we can discuss it here. I don't even think the concept has been. Are you sure
Can
the
I
concept
show
has
the
been
question
covered
from
so
my
far?
camera?
We are only left with 1 hour, and the problem is that we won't be. There's a lot left in this graph theory part, so we won't be able to cover that part. And it's a summary session. You will have a doubt session for it, for the graded
When will
assignment
it be?
and everything.
After its deadline is over.
Sorry, what?
After its deadline is over, then we will have the
No,
doubt
you'll
session.
have a doubt session before the deadline. You will have a doubt session before the deadline.
For week 10 only, no?
Yes.
Okay.
So I hope there's no doubt so far till this point.
Ma'am, I have one small doubt in what we were discussing. Ma'am, in the lecture there was a word called walk also, like with the path somewhere they were talking of walk. Can you just guide us?
Before you move on to the
I don't
topic,
remember the exact definition of a walk. I think it's and it's not
Walk, I think walk
that
defines
important for
the lowest
definition.
vertex from one point to another, sorry, one vertex to another vertex. If
You
there
can
may
check
be
the
from
definition of walk. It's the
before you move on to other topic, could you repeat this adjacencies because there was kind of a discussion away from the topic for a while. Could you please repeat this
adjacency lists.
Yeah. Thank you.
Okay, so this is the walk that you're talking about. If you can just look up the definition on Google, it's not a big thing. And I don't remember the definition right now.
No problem, ma'am. No problem. Thank you.
Okay. Then
Excuse me.
for the adjacency list is basically the collection of yes.
No, ma'am. I wanted you to clarify an adjacency list only.
Sorry, I couldn't hear you. Sorry.
No, ma'am. I had my doubt on adjacency list only, but you already started explaining. So.
Yeah. So I just first. But adjacency list is basically the for V1, it's this whole thing. The list is the whole of it. So we haven't done it for other vertices, we've only done for 2 vertices here. So V1 is it's the collection of the vertices that you can reach from V1. So from V1 you can reach V2. So this set has only V2. And from V2 you can reach V3 and V4. So this set has V2 to V4. V2 and V4.
Ma'am, can you explain what is planar graph?
Rishi, I think we are
Let's
skipping
just
the
not
topic.
jump to
Hold on.
things. We're discussing things one by one. Okay, is the definition clear of the adjacency list?
Yeah, thank you.
Yes, ma'am.
Okay. So is there a doubt regarding adjacency lists?
No, ma'am.
Okay.
Then, I mean, is there only a subtle difference between reachability and adjacency list? Did you understand? Or I didn't get the concept clear.
is a
I don't know. I'm not hearing your voice
Ma'am,
properly.
you
It's the
are,
same thing with others.
ma'am, you are
Reachability
lagging
is
a lot.
basically
Ma'am, your voice is not clear.
can you
Your voice
reach
is breaking.
reachability is can you reach V4 from V1? Can you reach V3 from V2? What you can now is
Okay.
it better? If I join again, it will take a lot of time. We're not left with a lot of time. Is it fine now?
Okay. Yeah, it's getting better. It's better now.
Okay. I'll try to speak a little louder then if that's an issue.
Okay.
So adjacency list is basically the collection of vertices that you can reach. So obviously adjacency list is related to reachability, but it's not. Adjacency list is the collection of it, and reachability is basically an idea.
Okay. Yeah. Thank you.
Adjacency list helps you
Can
figure
we
out this
say
idea.
reachability? Ma'am, can we say reachability the vertex which can directly connect it to another vertex?
It doesn't have to be direct. There does not have to be an edge. You just need to figure out if you can reach that point from here. And adjacency list, it's basically the outgoing ones. So you don't collect the reachable, you don't collect the points that are reachable. Okay, let me just make this clear. You don't collect the points that are reachable from here. Rather, you collect the points that have from. So if you can go from V2 to, why do we have a V2 here? It should be V3.
Like outgoing
So you can,
vertex count all
yes.
the outgoing vertex.
So there should be a vertex directed from V2, sorry, an edge directed from V2 to V3 and V2 to V3. Reachability is, you can figure out reachability from here using adjacency lists, but it's not the same thing, obviously. Is it fine now?
Yeah, thank you.
Let me just repeat this thing. If there's a confusion. In adjacency lists, you only put the elements or the vertices that are directly connected to this one by an edge. There should be, if you're putting V1 here, that means there is an edge from V1 to V2. There's an edge from V2 to V3 and V2 to V4. That's the adjacent list. And for reachability, there need not be have there need V1 to V4, but that's still V4 is still reachable from V1. I hope that's fine. Okay, then you have the number of. So this is not something that's very important, but I'm still writing. It's a number of edges, and there are two cases here. So one is the directed graph case, and the other one is this is the undirected one. So for the directed graph, you have n minus one number of edges. So by n minus one number of edges, we'll discuss it. And from here, for the undirected graph, you have n minus 1 by 2. So if you have, let's just say you have these, so you can have an edge here. Maximum number of edges can be, this is the maximum number of edges that can be there in a graph which has n number of vertices. So if n number of vertices are there, then the maximum number of edge in a directed graph can be n minus 1, and in an undirected graph it's n minus 1 by 2. So how does that happen? It has 4 vertices here, so you can only connect this, and you can't connect
Your
this
voice
to
is too
itself.
much is breaking.
That's why
Your voice is
is it
breaking
clear
too
now?
much.
Is it better now?
Now it's
Yes,
like
Is it
okay.
still breaking?
Yes, ma'am, it's better.
Okay. So if you have, so you can't connect, you can connect this to all the others, and then you can connect this to all the others, like this one, and then you can connect this to all the others, but you can't connect this to, so that's why there's n minus 1 number of edges. Otherwise, if you could connect this one to itself, there would be n square number of edges. But since we are not considering an edge from this to this, we don't consider this case at all. That's why there are n minus 1 number of edges. Is this part clear?
Yes, ma'am.
Okay. And then we have an n, because these are directed ones, right? These are directed things, so you'll have n minus 1 things. And here in an undirected one, so number of edges. So if there's an edge from here to here, you can have, and let me just clarify one more thing. So let's just say these are two vertices A and B, and you have an edge here. So these two are counted as two distinct edges. So we don't make it like this, we draw it like this way. But these are considered two different edges. This is not the same edge. One edge is from A to B, the other edge is from B to A. So in a directed graph, they are considered two edges. But in an undirected graph, they are considered to be one. Here you'll consider it to be one edge. That's why you have an n minus 1 by 2 here. But here you have an n minus 1. Is this part clear?
Yes.
Why we're dividing with a 2 here? Because these two edges will be considered only one edge if this graph was undirected. Okay. Then we have the BFS DFS thing. So for reachability, coming back to the reachability thing. So to find the reachability of a vertex from some other vertex, or to find which vertices can you reach from a given vertex, what you do is you try out two approaches. So one is the BFS approach and the other one is the DFS. First discuss the BFS one. BFS is breadth first search. Breadth first.
These are types of reachability.
What you do here is, let's just say you have a graph. We just draw the graph first and then we'll discuss what it is. Let us say you have this graph. So breadth first search is a way to figure out reachability. You do understand what reachability is, right? It's an idea if you can reach which vertices can you reach from A. Let's say you can choose any vertex. Which vertices can you reach from B? That's reachability. And breadth first search is the way which you can use to figure out reachability. So this is like an option that you can use to figure out if B is reachable from A, if E is. So this is a method to find reachability. Is it okay? And now we'll discuss what the method is. So how do you find which vertices are? BFS is a search where you try to find which vertices are related to any given vertex. So let's just say you're choosing the vertex A and you need to figure out which vertices can be reached from A. Right? So we start from A. What we do in breadth first search is we first figure out all the vertices. So there's something called, first we figure out all the vertices that are directly connected to this. So you have B and then you have C directly connected to it. And there's no other vertex which is directly connected to A. Then we pick one of them and then see which one are connected to those. Let's just define the Q first. Because to discuss this method, we need to know what a Q is. So a Q is basically this collection where you put elements. We'll discuss how we do the breadth first search. So what you do here is you're starting your search from A and you need to figure out which vertices you can reach from A, right? So you put an A here first. And then you see B is reachable and C is reachable. Reachable and not reachable, there is an edge from till B and till C. So you write a B and C here. You can't write E because there's no direct edge from here. And then you first, now you can choose whatever, but if you put B first in the queue, then you will start things with B. And then you go to this vertex B and see which one are directly connected to this. That means which one has an edge from B. So it's C, but C is already being covered, so you don't need to write it. And then you have E. And then you suspend this, you just remove this thing because this has been covered, right? So you can move it out. move it out in the sense this one's putting a cross here. This is not a usual thing that you do. I mean, you don't have to put a cross. It's for your own sake that you do the right thing. This has been covered. That's why we put a cross there. So this has been covered. Now there are no direct edges from B. And then you go to the C one.
Ma'am, shouldn't you do the same thing to A? Because now you've crossed A also.
Yeah, you can. That's why I said this is not a standard practice. You don't need to do this. We're only putting a cross so that we know that this has been covered. And there's, okay, let me just define two other terms too, because we'll be using them very frequently. So one is visiting and the other thing is exploring. So when do we say visited instead? So we say that a vertex is, let's just say you go from here to here. So we say B is visited because you've visited B. And if every direct vertex that is connected directly to A is visited, then we say that A is being explored. So while we put a cross here, I put a cross here because it has been explored. Is the difference between visited and explored clear?
Yes.
Because we'll be using, this is not something that you'll be asked, but we'll be using these two terms very frequently. So you should know what visited means.
Could you please repeat that part? Sorry for that.
Okay. Visited means if you start with A, then A is already visited. Then you go to B, then B is visited. And if you've written B and C here, that means you've explored A completely. Exploration means that you've visited every neighbor. Neighbor means this thing, directly connected vertices. This is directly connected. This is also directly connected by an edge. So if you have explored, if you have visited every neighbor of A, then we say that A is explored.
Oh.
Like in this case, you've visited B and then you visited C. So A is explored now. That's why we put a cross here. This is not a standard practice. You don't need to do this. And then B.
Sorry to interrupt. Can I say something?
Yes.
Ma'am, can you say for BFS in Hindi? In Hindi, if you can say something in Hindi about the BFS, which will be helpful for us. Just one line, and so that we understood the BFS completely.
Okay, so I can't explain the whole. This is the process. BFS is a method. So I can't explain the whole thing in Hindi. I don't think everyone understands that. Right? If you want to just say something about it, we can do that.
Something about, yes, not a complete thing.
Something that defines it, okay.
Yes.
BFS के अंदर बेसिकली एक मेथड है कि रीचेबिलिटी का मतलब होता है कि आप किधर पहुंचना चाहते हैं, आप किधर किधर पहुंच सकते हैं. ए से अगर आप स्टार्ट करेंगे तो कौन कौन से वर्टिसेस पे आप जा सकते हैं, उसका मतलब होता है रीचेबिलिटी. एंड बीएफएस एक तरीका होता है रीचेबिलिटी को पता करने का. रीचेबिलिटी एक आइडिया है ना कि आप किधर किधर पहुंच सकते हैं, ए से स्टार्ट किया तो कहाँ जा सकते हो. तो बीएफएस उसको करने का तरीका है कि आप किधर किधर जाने के लिए तरीका भी तो चाहिए ना. तो ब्रेड फर्स्ट का मतलब हो गया, ब्रेड का मतलब होता है ऐसे डिस्टेंस, राइट. सो व्हाट यू डू इज आप ब्रेड के अंदर सर्च करते हो पहले कि ये सब कुछ कवर कर लिया. डेप्थ का मतलब होता है डेप्थ में जाते हो. आपने यहाँ से स्टार्ट किया, आप यहाँ पे गए, इंस्टेड ऑफ गोइंग टू सी फर्स्ट आप पहले डी पे जाओगे क्योंकि आप.
यस मैम.
तरीके होते हैं रीचेबिलिटी को पता लगाने के कि आप रीचेबल वहां तक पहुंच सकते हैं कि नहीं पहुंच सकते इस ग्राफ के थ्रू. इज इट फाइन?
Yes, ma'am. Thank you so much, ma'am.
Ma'am, I have a question here. Ma'am, we took A, B, C, and E. That's fine. But from A, we could have gone directly to C and then come to E, or from A to C and then we could have gone to D.
We're discussing it. What you do is in the breadth first search, if there's one thing here, and let's say this is it, B, C, D, and then you have a E here and then an F here. So what you do here is you first cover everything that's initiated from A. So you cover everything. This. You can't directly jump to this one. That's what breadth ka matlab is this, that you're covering all of it. If you look at it this way, is that all right? That first you cover everything that directly has an edge from A. And then you move to other parts. F and A do not have a direct edge, right? You can't jump to F. You can't jump to E directly. In a breadth first search. Is this fine now?
Yes, ma'am.
If I had to clearly picturize this, it's like this thing, that if you have four things here, B, C, D, E, and then you have say two things here, two things here, three things here, two things here. So you start with A, then you go to B, C, D, E, but you can't go to these ones. You can't these you'll explore from here. You can't directly explore them from A, right? Because A and B do not have a direct edge. If you had an edge here also, then you could explore this too. Then you will put F also in this queue. Is this fine?
Yes, ma'am.
That's why it's called breadth first search, because you're exploring the complete breadth first. Breadth is this thing, covered everything, which can be directly, which has a direct edge with A, and then you move to other paths. So B is here, C is here, so A is explored. We put a cross here because A is explored, and then you look at B. So we go to B, and then we see that B is connected. When I say connected here, I mean B has an edge to C and it has an edge to E. So C is already here. You don't need to write it again. Then let's just write E here. And now B is also explored because every vertex is reached, right? Every vertex that is directly connected to B has been visited. So it's explored. B is explored. So we put a cross here too. And then we go to C. And then from C you go to D. Let's just continue the list here. And then one important part that you need to keep in mind is, okay, we'll come to that later. You go to D, and then C part is, so C is also explored because C only had one edge here, and that has been visited. So every neighbor, let's just call it neighbor, every neighbor of C has been visited. That's why C is explored. Then we remove C, and then, okay, E is already in the list. And then you go to E. So this is what you have to go next to. If this has been explored, then you go next to this one. That's why we are keeping a list of all these things. Then you go to E part, and then this has no outgoing edges, so this has been explored. And then you go to D. So D is also explored because there's no outgoing edge. So this is the order in which your BFS thing works. Is this fine?
Yes.
What you do here is you keep, this means you've removed it. Removed in the sense that this has been explored. So you need to make sure that if this thing enters first, let's just say B entered first and C entered after it, then you explore B first. And then you go to C. And then you go to E. This is the order in which you explore. So this is, sometimes we call it first in, first out. First in, first out means the one that came first in the list would go out first. So this is called first in, first out search. Is this part clear? The BFS search?
Yes, ma'am.
Okay, so just to give a recap of this, what you do here is you start with A because you would be given the vertex that you start with. So if you're given A, you first write A, and then that's why because these terms are extremely important, we are using it over and again. So you should know what they mean. Visited. So visited means you have just gone there. And explored means you have visited every neighbor of it. That means it's explored now. So you start with an A, the neighbors are B and C. So you put a B and C in the stack, the queue, and then you go by this order only. So if B came first, you can write C as well. There's no problem. There's no condition. You can write C here and then D here. No problem in that. But then you will have to explore C first. To explore B first. When B is done, when B is explored, then you move to C. Then you move to E. Is this fine?
But why are we going to E instead of D?
Sorry, what?
We are going towards C after reaching C. Is there kind of that we move towards E instead of D? Why is that?
E instead of, I don't think I understand what you're asking.
No. After exploring A, after exploring B, once we reach the point C, then we are exploring E. Why not? We are exploring. We are moving
Because
towards.
E came first in the list.
Oh,
That's why we are keeping a list here. That's what I'm saying. that in the breadth first search, you follow this list. So no matter which is the next one, if B comes after C, doesn't mean you'll start exploring B first.
Okay.
E is first in the list, so you'll explore E first, and then you'll go to D. That's why we are keeping a list here.
Okay. Thank you.
This is called a queue. So and then there's something called BFS tree. So BFS tree is, you start with this thing. You start with A, then you have B and C here. And then you start with B. With B, you have E. One thing that you need to keep in mind is you don't connect these two in a tree. So I'll tell you what a tree is. Let's just discuss what a tree is first. So tree is basically where there are no cycles. So if there's no cycle to it, then it's a tree. Just give me a sec. It's basically, to discuss a tree, you'll have to discuss connected sets too. We'll discuss BFS tree later. Let's just do the basics and then we'll discuss BFS and DFS both in detail. The trees and every part of it. Or let's just start with because to discuss BFS tree, you first need to know what a tree is. Then for that, you need to know what a connected set is. So let's just start with a connected set. So connected set is basically if you have connected means if you can reach, let's just say you have this thing and then you have this thing here. These are all vertices. So this is, and then you have this thing. So this is a connected set because from here, let's just not put directions here. It will complicate things. From this vertex, you can reach every other vertex, right? You can reach this thing, you can reach this thing, and then you can reach this thing. So here you check for reachability. So if you can reach from every vertex here, if you can reach every other vertex, note that I'm using the word reach, we are not talking about a direct edge. We don't have a direct edge from here to here. But it's still a connected set. So connected set means that you need to have reachability from every point to every other point. So you can reach from this point, you can reach every other point. And similarly, from all of these 4 points, you can reach all of the other 3 points left in this thing. But you can't reach this point from here. This is not reachable from here. That is why it's a different set. So this is called a connected set. Connected set means if you can reach every vertex from every other vertex, it's called a connected set. Is that okay?
Ma'am, one doubt, ma'am. In this connected
Yes.
set means in the graph, all the vertex should connected to all the vertex. It means all the vertex should be reachable to another vertex, right?
Yes, reachable,
If
not a
one
direct
vertex
edge. You don't need to have a yes.
Yes, ma'am. Ma'am, in the entire graph, if one edge is not connected with another, means it is maybe directly or it's not reachable to another one vertex. Means can we say it's a connected set?
If it's not connected, let's just say.
Ma'am, in a set of over a 5 vertex, ma'am, 4 vertex connected to all the sets. Sorry, all the vertex.
Okay.
But the remaining one vertex doesn't connected to one vertex. Means what will be?
It doesn't matter. Let's just say I'm not drawing all of it. Let's just say these 4 vertices are connected to all the other 3 here. And this one is not connected to one of them. Let's say this is not connected to this one and it's connected to all the other. It is still a connected set. It's not about the direct edge. I'm repeating it again. This is not about edge. You don't have an edge here. Do you see? There's no edge here, but it's still connected. You can even remove this thing. If you remove this thing, it's still connected. Because our ultimate purpose is to reach from every vertex to every other vertex. That's all. Is it fine now?
Ma'am, yes, but you are saying, ma'am, in this case, you're just giving a undirected, right? I mean, what if it's a directed edge?
So if it's a directed one, let's just say this is this thing. Then it's pretty obvious that it is not connected because you can't. It's about reachability. This is the keyword here. So if you can't reach, you cannot reach this point from this point. So this is not a connected set. Is it fine now?
Yes, ma'am.
Okay.
Yes, ma'am. Ma'am,
This is the connected set.
one other doubt, ma'am. In this connected set means all the vertex should be reachable to all the vertex, right?
Yes.
If one vertex is left means also it's not
in the
considered.
connected set. Yes. So if this is not a directed graph, then this is a connected set. This is also a connected set. This is also a connected set. But if it is a directed graph, then it depends on the directions. Okay. And then we have another thing called components. So components means your maximal connected set. Maximal connected set means, as in this case, this is the maximal connected set. Maximal in the sense, even if this edge was here, it is still the maximal connected set. So what you do here is, you find you cannot have any other edge included in this set, right? Because then it won't be connected. If you take this one, you can't reach any vertex from here to this vertex. So components means these things. These things here are components, the maximal connected set. Also, if you will consider only these three vertices, let's say, so this is not a maximal connected set because this one you're leaving this one. Maximal means every vertex that's reachable from all these three vertices should be included here. Is that all right? So if you have this thing here, and then you have this thing, and then if you just consider these three, 1, 2, 3, 4. If you just consider 1, 2, 3, 4, then this is not a maximal connect. It's a connected set, obviously, but it's not a maximal connected set because you're leaving the fifth one. Is this fine? That's a component for you. So here we have three components: first component, second component, and third component. And for the directed one, you need to make sure if you have this thing, then it's a different case altogether. It's so you will have to see if you can start with one and see if you can reach all the other vertices. So you can reach 2, you can reach 3, you can reach 4 and 5. And then from 2, you can reach all of them. From 3, you can't reach all of them. So this is it's not a connected set. Is it okay? And then let's just discuss what a tree is. So tree is basically when you discuss a tree, let's just say that this is a graph and you need to find if this is a tree or not, right? Let's just see if this is a tree or not. This isn't a tree because what a tree is basically it's a connected set, but it should not have the unnecessary edges. So it's a connected set minus the unnecessary edge, which is not required to make it connected. So what happens is, let's just draw more edges. If you have this thing, if you will remove this thing, it's still connected. If you remove this thing, it's still connected. So this now, if you remove this thing, now it's not connected. So a tree is the minimal connected set in this sense. Is this clear to everyone?
Yes, ma'am.
I need a response if this is clear or not. So let me just repeat this again. If there are these, if you look at these edges, these edges, this one, and this one, these are unnecessary edges. You don't need these edges for this graph to be connected. Can you see that? No one's responding.
Yes, ma'am.
Yes, ma'am.
So we can
Yes, ma'am.
remove this edge. You can remove this edge too. You can remove this edge too. This one too. And it's still connected. But if you will remove any other edge now, it won't be a connected set. So that's, in that sense, it's a minimal connected set. That's a tree for you. So this is a tree. So for tree, you say that you won't see any cycles here. We're not defining cycles yet. Cycles, okay, let's just not go there because it's not required for the BFS, DFS that we were discussing. So coming back to the BFS tree, what a BFS tree is, we had an example there. Let's just draw the BFS tree here.
Ma'am, if there are extra connections, then we won't consider it as a tree, even if they're connected.
Tree is the minimal connected set. That's what I'm saying. So if you have something, if this is extra, this is not a tree. Just remove this thing from here. Because you don't need it for this to be connected. And let's just say you have this thing. You can't remove. You can remove this edge because this is an extra edge. You can also remove this one. It's still connected. This is also a tree. But you can't remove this edge. This edge you can't remove. Because now it becomes disconnected. Is it fine?
Yes, ma'am.
One very clear way to figure out if it's a tree or not is you should not have something, a closed thing should not be there. So if it's closed, it's obviously not a tree. This is a closed figure here. If you see anything closed, even in this one, it doesn't have to be a triangle. If you see this is not a tree. You need to remove one of the edges, not two. But this is the tree then. So for the BFS tree, we're making the BFS tree here. What you do is you start with A, obviously, because the search starts at A, and then you go to B and C. So note that B and C these are called levels. So this is level 0. This is level 1. They're on the same level. That means they are immediately after visiting this, you visit this. Okay, you don't directly jump from B. You have already reached B, but instead of going from B to E or something else, you go to C. Because you want to make sure that every vertex to A directly connected to A. That means which has an edge from A is covered. So B and C first, and then because you listed B first, so you start with B. And then B, so you don't list C here again because C is already listed. So don't repeat a vertex in a tree. Because C is also connected to directly, there's an edge here. That doesn't mean you'll make a C here. You don't need to repeat. In fact, you should make sure that you don't repeat anything. Otherwise, it's wrong. So after E, C is done, and then you go to C. So the exploration part of B is done. Then you come back to C, and then that's D here. So this is it, and everything is covered, right? A, B, C, D. So this was something which is connected. It is connected. That is why there is a tree. If this was not connected, let's just say that if there's no edge here, then you wouldn't see an edge here as well. So that means this is not reachable. So from that means you wouldn't have an edge here. So from the tree, you can just see that because D is not a part of this tree, D is not reachable from A. Is that okay?
Ma'am, can we say that A is connected to B, then B is connected to C, and D under C, D is connected. This tree is equal to
Connected is a word
one.
that we are using. Okay, wait. Let me just clarify this thing. Connected, we're repeating this word connected, but that's a very informal term. It's not a formal maths term that's used here. So don't use connected. I don't want to repeat over and again that there is an edge between A and B. There's an edge from A to B. That's why I'm saying that they're directly connected. Otherwise, directly connected is not a term.
Ma'am, we should say it's an edge.
Yes, you should say that there is an edge
Yes,
from
ma'am.
A to B.
Edge.
Because it's
Yes,
very
ma'am.
long, I'm not. Yes.
Yes, ma'am.
Is there a doubt?
Ma'am, what you've drawn is that you consider, ma'am, now you had drawn a tree, ma'am. Now we can draw A is A has A and A to B have a edge, and B to E have a edge, and B to C have another edge, and from C we have another edge for D. We can consider these two trees are equal.
You're suggesting another tree. Are you suggesting another tree? This is the only tree here. But if you'll change the order, if you'll take C here, unless you don't change the order here, the tree is not going to change.
No, ma'am.
And you can't connect it. You can't connect B and C. Because that's not even a tree.
Ma'am, no, I'm not connecting, ma'am. Ma'am,
Okay.
can you draw what I say now?
Okay.
A is an edge to B, where B has two edges for two vertex. One is E and another is C.
That's so when we say
No.
this is not, we're
From
discussing
C and
BFS tree. You can't put C here because
why,
first
ma'am?
you'll cover everything that's connected to that has an edge from A. You can't put C later. That's what I'm repeating
Oh,
again. This is a very
yeah, ma'am.
important
Now I
aspect
got
of
it.
Ma'am, if
BFS
the
tree.
starting point is B,
Now I got it,
Starting
ma'am.
point. The starting point is A. That's where you start your search from.
if it were B, like A was never there, so B, C, D, E, F, like that.
You want to remove A. If you start your search from B, you'll get something else, obviously. There's not enough space, otherwise I'll do the B part here. You want me to do the B starting from B as well? If you have a
No,
B1, let me
okay, I got it.
for B, you'll start with B and then you'll go to C and then E. Because there are two things here. And then you'll go to one of these. So you've mentioned C first. So you'll explore C first. So from C, you'll go to D. And then you'll come. Okay. These, I've already said that you can't keep going. If there was an edge from D to say, if there was an edge here, that doesn't mean you'll go from D to F. You can't do that in a breadth first search. You'll have to follow this order. So you'll have to make sure that every vertex here is explored. That's why I was putting a cross here to make sure that every vertex has been explored.
Ma'am, in this example, which now you have taken, ma'am, in that case, the node A will never be visited.
Yeah, it will never be visited, right? From B, if you start, A will never be visited.
Okay.
That won't be the part of the BFS tree as well.
Yes, ma'am. Okay.
That means A is not reachable from B. That's what
Okay, ma'am.
that's why we are doing the breadth first search, right?
Okay, okay, okay.
That's your breadth first search. And then you have the depth first search. Okay, let me just do one example, do one thing here. That's also important. So let's just say this is a BFS tree. Let's say you have this thing. So this is, I've already explained this. This is level 1. Although when you start, you go to B first, then C, then D. But these all are level 2 things. This is called level 2. All of these are level 2, B, C, D. And then this is level 3. Okay. So if you are asked, so let me just say that this is the given tree to you, and you are asked if there is an edge from A. So this is the tree. This is not the graph. Graph is something else, right? There might not be an edge from A to F, but can there be an edge in the original graph? That's the question, right? If you say that can we have an edge from A to I, this means there's an edge. Yeah, let's just directly write it. Can this be an edge in the original graph? Or can this be an edge in the original graph? Or can this be an edge? So we're trying to test if these can be the edges. So if you have A, say, and you want to test it A and I, so I hope you're clear that BFS tree and the original graph are not the same things. We've seen it here, right?
Yes, ma'am.
This is the tree and this is the graph. They're not same. So
yes,
here when you see, you have an edge from, from A to C, from B to C, you have an edge here, but here you don't have an edge from B to C, right? So that means you can have, there's a possibility that you can, if you don't see an edge here, there could be an edge here in the original graph. So that's the question here. The question is, can you have an edge? We don't see an edge from A to I here. But can there be an edge from A to I in the original graph? That's the question. And the same is with these things. So if there were, so this thing is, what do anyone wants to answer this one?
Yes, ma'am. A to I not possible. Otherwise, next to D first we'll write I.
Yeah. So you'll write I here on this level 2 thing. So this is not a possible edge. And then is this an edge? A possible edge.
Could be, ma'am.
Ma'am, I think it's possible.
It is possible. And then the BG one.
No, ma'am, not
Bit
possible.
confusing.
Otherwise, under B first we'll write G.
Yeah, because although they are on the same levels, but I've already told this that you start with the one that you write first. So if you write B first and G, if there was an edge from B to G, you should have written G in this one. And since you've written it here, that means there's no edge from here. So this is incorrect. And then there's C and F. Let's see if there's
Ma'am,
one
how
from C to F.
E to F?
What?
E
E to F?
E to F.
So you can have an edge from E to F because if there were an edge, let's just say the original graph is this. Okay, let's just say this is the graph. Then how do you do the search? You go to B and then you go to E and then you go to F. So F has already been explored, and I've already said that if F is already being explored via B, then you don't have to have an edge from here. You don't repeat the things, right? Like we did here. Some element is C was already explored from here, no? C is already explored from A. That's why there's no edge from here to here.
Sorry, ma'am.
That's why we
From where
don't.
to where?
In a B, what you do in a BFS tree is you don't see A and C has an edge. Can you see A and C has an edge, and then B and C also has an edge. So if you look at this graph, this tree, if you look at B and C does not have an edge in this tree, but they have an edge here, right? What I'm trying to say is that if C is already explored via A, you don't draw an edge here. That's the rule of the tree, right? Because we want to keep it minimally connected. So we can't draw an edge here. So in a tree, there won't be an edge, but in a graph, there can be an edge, no?
Okay.
Is it clear now?
Yes.
Okay. And the last one that we have was C and F. Let's see if there could be an edge from C and F.
Ma'am, this is also not a graph. Now then how you are so sure E to F? As you said, it is not compulsory,
They're
na?
only asking the possible edges. They're asking if there can be an edge, possible edge. Is the
Okay,
question.
which can be or not.
We're not saying that there is an edge. Okay. So
Not
is
possible.
C and F possible? It is possible, right? Because C and F is possible because F has been, let me just remove this thing first. Because F has already been visited via B. So even if C was directly connected to F, you won't write it here because that's the rule of tree. You don't write vertices again. Is that fine?
Yes, ma'am.
Yes.
So this can be an edge. Okay, so discuss this part and then we'll come to the DFS one. So what happens in a depth first search? Let's just draw the same one so that you can just compare the two things. A, B, C. In the original one, there was not an edge here, right?
Yes, ma'am.
This was the original graph. So let's just try this search. So this is another way to find reachability. This is another method. One we've already discussed. Second one is this one. So how do you do this one? In this, there's a similar thing here, but it's called a stack here. Here we call it a stack. There we were calling it a queue, right? So what do we do here? First, we start with this. Let's just say we start again with the A thing. Because I want you to observe the difference. So let's just start with A. we put A here, and then instead of going by the depth, the breadth would mean covering every vertex which has an edge with A. So like this, and then if there was something else, you would also consider that. But when you talk about depth, what you do is you don't consider, so you go to B and then you directly go to what is connected to B. And then from that point to something else, if there is a connection. And from that to something else, if there is something. So you keep going in the depth part. Is the idea clear? So what you'll do here is,
It's clear, but the exact difference between the BFS and DFS.
yeah, you see the difference now. You put B here first. So you go from A and then you go to B. And then notice that A has not been explored yet because C is still left. But we still go with B. So before completing the exploration of A, we're trying to visit something that is connected, that has an edge with B. So we'll go to C then. We can go to E too, but we're going to C first. And then we'll go to D. And then we'll see that it ends here because there is no edge from here. So we'll come back to D. So notice that D has been explored. So we put a cross here. So in BFS, what we were doing is we were starting from here. What we were doing is the vertex that comes first would be explored first. Here what you do is the vertex that comes at the end, the vertex that enters the last will be, we don't explore it completely, but we cross it when it's completely explored, right? So this would be taken first. Is the difference clear? That's one
like
of the
the
major
reverse.
differences. Sorry?
It's like the reverse.
Yes.
Right.
It's, don't look at it as the reverse, just look at it as if it was this thing. So you follow this order. You go from A and then you start with B. So you start exploring B and then you go to C and then you go to D. But this wouldn't be in order. This wasn't the order in the BFS search, right? The order was something else. This is according to the DFS one. So you remove, this is called last in, first out thing.
First out.
Yes. So the one that enters the last would leave the first. This stack. This means
Can you teach this again, DFS?
DFS, we're not done with DFS. We'll do it. We're not done with it yet. So D is explored completely because there's no edge from D anywhere else. So then we'll go back to C. So the last one here is C. Because D is already out. So C is here. From C, you'll see you can go to E. So let's go to E. And then from E, you can't go anywhere else. So E is also done. And then you come back to C again. And then you see that C, yes.
Ma'am, like here A.
If you'll keep, that's one advice, if you'll keep interrupting over
Sorry,
and
ma'am.
again, you won't be able to understand because it breaks the flow then. So let
Sorry.
me just complete first and then you can ask. So I myself forgot where I was. So E we did, and then E was out, and then we went back to C because C is the last one here, right? So we go to C then, and then C is also explored. So it has D, it has E, and then nothing else to visit from here. So cross C as well, and then you go to the B thing. So B has nothing. B has E, but E has already been explored. So we don't go there. So we cross B as well, and then we cross A. So that's your depth first search. What you do here is in the depth first search, you started with A and then you went to B, right? And then after B, you went to C. You could have gone to E also, but we're taking C. You go to C and then you go to D. And then from D, you go back to C. And from C, you go to E. And then from E, you go back to C because there's nothing to visit from E. So go back to C. And then there's nothing to visit from C. So go back to B from where you came. And then from B, there's nothing to explore from B. So go back to A. So this is your tree. Is this fine? Now you can ask your doubt. Someone had a doubt here.
You
Ma'am,
can
ma'am,
get it from
okay.
the stack that you are make, like C is connected to E. It can be like D is connected to E by the stack that you make.
What is the exact question?
Ma'am, the question is, if the graph is not given to us and this is the only stack is
That won't
given to us.
happen. Stack is something that you use to solve this. This is something that you're using. This is your idea. It's not graph is the question. You'll be given the graph. In simple words, graph is
Okay.
always given. You won't be given stack and then you won't be asked questions. At least no, you won't be asked to draw this. And even if you're asked to, because look, by just looking at the stack, you don't know which one came first and then which one left, and then because there's ordering too here. We keep a counter too. We'll talk about that too. The counter thing, but I don't want to go into that thing now. So I hope this part is clear.
Yes, ma'am.
The DFS search is clear. Okay.
Yes,
Then
ma'am.
moving on to the other part, we have and also there's one small thing that I need to mention. The tree has, so when you have a tree is a minimal connected set, if you remember. So if you have, let's say, n vertices, n number of vertices, then how many edges would a tree have? So let's just say let's just say that it's a connected thing whole, and then we want to figure out the maximum number of edges that can be there to make it. Obviously, let's just say there are 4 things, then, or let's just say there are 5. So what are the number of edges that you need to make it a tree? That's one question. So if you have n vertices, then your tree, so let's just see this one. If you have 3 vertices, you'll have 2 edges here. It's a tree, right? In fact, this is the only tree. You can't have any other tree in this case. If you have 4 vertices, then you can have this tree, or you can have this tree, or you can have others too. So these are trees, right? If you have 5, then you will have 4 vertices. If you have 5 things here, then you'll have this thing, right? So we are leaving this because this is not needed. Now this is not a tree. If you close it, this is not a tree. We've discussed it. Because this is an unnecessary edge. An unnecessary edge is not needed in a tree. If there's an edge which is not needed for the connected set, then it's not a tree. So n vertices are there. So the number of edges would be n minus 1 in the tree. Is this okay?
Yes.
And then we're moving to cycles. What are cycles? So when you discuss of cycles, it's like this thing. So in an undirected graph, this is a cycle. Or you can say, let's just say you have a vertex from A. Let's just say this is A, B, C. Number it as 1, 2. It's 1, 2, 3, 4. So this is a cycle here. This one is a cycle, right? And if you have, we're discussing it for the undirected first, and then we'll discuss it for the directed case. And okay, so if we have this thing, so and if we take this thing, this, and this is also a cycle, right? 1 to 2 to 3, and then to 4, and then to 2. This is also a cycle, right? This is a cycle. This is a cycle. There's a difference between when you take 1 to 2 and then to 3 and then back to 2. So this is called a simple cycle. So a simple cycle means that only one of the vertices is being repeated, and then you have other cycles where more than one elements are being repeated. One vertex is repeated. Like this one, let's just say you have 1, 2, 4, then you have 6, and then you have a 4 again, and then you have a 2 again. So if this is a thing, this would look like you have an 1, 2, then 2, 4. Let's just draw a 6, 2. A 6 here. You can't go from 6 to, okay. If you go from 4 to 6, let's just take 3 here. A 3 here, and then a 4 again, and then a 2. If this is a thing, then this is not a simple cycle. By this simple cycle means that only one of the vertices is repeated, and it's a simple thing like this one, simple one. But if you look at this, you go from 1 to 2, then you go from that to 4, then to 6, then to 3, then you come back to 4, then to 2. So it's a, there is one more thing, the edges shouldn't repeat in the cycle. So it's again not a cycle, because the edges shouldn't repeat. The edges should not be repeated in the cycle. So for a cycle, what you need is, you need the vertices to be repeated. One vertex repeated means it's a simple cycle. And if you repeat more than one vertex, if you repeat 2 vertices or more, 2 or more vertices, it's not a simple cycle. And it's not at all a cycle if an edge is repeated. So if you're repeating an edge like in this one, it's 2 to 3 and then 3 to 2. It's not even a cycle. We've given a wrong example here. You can take it this way. If you take 2 to 4 to 6 and then to 2. 2 to 4 to 6. And then if there was an edge from here to here, let's just say there's an edge from here to here. So 2 to 4 to 6 and then again to 2. This is a simple cycle. Is this fine?
Ma'am, what you said in the second statement, vertex one or more, not simple cycle.
Only one vertex is repeated, right? This vertex is repeated. What other vertex is repeated here? If this was something, yes.
In the second statement, you write.
This one?
Here, yes, ma'am.
This is not a simple cycle. No, if 2 or more vertices are repeated in your cycle, let's just say this is this thing, 2, 4, 6, 2, and then you go back to 4 again. But this is, if this is an undirected graph, let's just not take 4 here directly. Let's just take 5 first and then 4. So this is not a simple cycle, because that's not even important, but let's just discuss it anyway. So because there are 2 vertices being repeated, this is repeated and then this is also repeated. So this is not a simple cycle. And if you see an edge being repeated, like this one, if you see 2, 4 and then you see 4 to 2 again, then this is not at all a cycle. This is not considered a cycle. You have 2, 4, and then you go, so you go from here to here and then you come back here. This is not a cycle. Not a cycle. Is this part clear?
Yes, ma'am.
Okay.
Yes, ma'am.
And then you have something called acyclic graphs. Acyclic graph, as the name suggests, is a graph where you don't see any cycles. Okay, we forgot to discuss it for the directed graph, right? So for the directed graphs, cycles for directed graphs, where you do this thing. Let's just say, so let me just give you a very simple example. This is a cycle because you go from here to here, then here to here, and then this is the complete cycle. Let's just say this is 1 to 2, 2 to 3, and then back to 1. This is a cycle because this has directions now. So you have to be careful. And if you see something like this, what you do is, this is absolutely not a cycle. You go from 3 to 1, and then you can't go to 2. This just ends here. The cycle is, you can't continue. Is this part clear? This is not a cycle. Not a cycle. And this is a cycle.
So, ma'am, the second one we call acycling graph.
Yes, this will be considered acyclic because it's this and acyclic is which does not have a cycle at all. Acyclic graphs are no cycles. I don't think I need to write these down. I'm just writing so that it's there. Acyclic graphs are graphs with no cycles, like this one. This does not have a cycle. Now you should see a contrast between a tree, and you should know that tree and a cycle. So trees are always acyclic, that means, right? You have a tree, it can't be cyclic because if there was a cycle, it wouldn't be a tree. Cycle means this thing. And this is an unnecessary edge. So you can remove this one. This one. If there's any doubt, you can just ask. Because we're going really fast.
Ma'am, in acyclic, it will complete the cycle or not? As you are drawing, you are just lefting the one side.
Okay. So if you have something like this, it just means it shouldn't have a cycle. If you have something like this, and then you have this thing, and then you have this thing. So the problem is now this has a cycle because it's an undirected graph, so you see a cycle in it. This is a cyclic one. Can't call it an acyclic graph. But if you just make directions in, and then you do this. But this is not a cycle. There are no cycles in. This graph has no cycles. So this is an acyclic graph. Just so that there are no cycles.
Basically, ma'am, it depends on direction.
In a directed graph, it depends on the directions, obviously. But in an undirected graph, there are no directions, so it can't depend on directions. Depends on the type of graph you're dealing with.
Okay, ma'am.
Okay.
So, ma'am, if there is an undirected graph and it's a closed graph, then of course it has to be a cycle, is it?
Yes. If you see something flows like this thing or something else like this thing, then it's obviously a cyclic one.
Yes, ma'am. Thank you.
And then there's this thing so we've already, the BFS tree and DFS tree that you see are trees. I hope that's clear that they are trees. That's why we also call them, that's why we call them BFS and DFS trees. And then, so let's just talk about the edges now, types of edges. So they are majorly categorized into two. So first is the tree edges, and then there are the non-tree edges. The tree edges are the ones that you see when you make a tree, and then they're a part of that tree. Like you made a DFS tree and a BFS tree. So it depends on what method are you following. So if you're following the BFS method, then you will make a BFS tree and see if it's a tree edge or not. So if this, like, look at this. So we discussed this graph. Yeah, this was the BFS tree and this was the original graph. So if you have a look at this, now this is AB is here and it's also in the tree. So it's a tree edge. But if you look at B and C, it's an edge here. But it's not an edge here. That means it's a non-tree edge. So I hope that distinction is clear. And then in the tree.
Ma'am, in this, can we say the non-tree edge is a cycle edge? Simple cycle edge?
Yeah. It depends on, again, it depends on if you have something like this, let's just say, you can't call it a cycle, right? So this can be a non-tree edge. In fact, this is going to be a non-tree edge. If you'll perform BFS here, this is going to be a non-tree edge, but it's not a cycle. This is not a cycle. We can't say that.
Yes, ma'am. Ma'am, can we say all the cycle edges, simple cycle edges or non-tree edges?
The cycle edges, yes, they are the non. If obviously, because they can't, non-tree edges are when you make the tree, those edges should not be in that tree. So if this is this is the edge which is a part of the cycle, it can't be in the tree, right? one of them has to be missing from the tree, depending
Yes,
on where the
ma'am.
search starts from. So if it starts from here, some different edge would be missing. If it starts from here, some different edge would be missing. Right?
Yes, ma'am.
It also depends on BFS and DFS. Okay. And then here you have three categorizations of this. So first is okay, before discussing the non-tree edges, we need to know some other concepts as well. Let's just start with them first. So when you have let's just take up an example of a DFS case here and how we maintain a counter. So we're discussing a counter here to discuss the non-tree edges. What is a counter? We discuss of this in the context of DFS search, depth first search. So let's just consider this example. Let's just consider this thing. And what you do here is, so you obviously would make a DFS tree, but this time we'll maintain a counter and I'll tell you what a counter is. So you start from, let's just say we're starting our search from, should we start from, okay, let's start it from 2 this time. So if we start from 2, our search, I hope you remember why we're doing all this. The BFS DFS thing is for reachability and there are other purposes too. So BFS DFS is a method of finding the reachability, but they are used for other purposes. We'll discuss those too, but for now we'll just discuss this thing. So from 2, let's just have the directions to them. From 2 you go to 0. And then there are 2 ways to go. Let's just go this way. Then you go to 5. And then how do we maintain a counter? I hope that we don't need a stack here. It's a good habit, a good idea to keep a stack here to be more clear of things, but you can do it without a stack. So if it's getting confusing for anyone, they can just tell and we can make the stack too. So, but for maintaining, what we do here is we start from 2 and we started doing the things. So we put a counter 0 here. This is called the pre number. So when we write this thing 2, 0 and something here, some other number here, say n. So this is the pre number, this is the post number. You don't need to know the terms, but because we'll use it in the discussion. So you put a number here 0, because you started the search from here. So it's 0. And then you went. And this number is when you start, when you visit the vertex. So when you visit 2, you put a number here. And this is the number that you put when you are done exploring this vertex. So this post number you put when you're done exploring the vertex. This pre number you put when you start exploring the vertex. We start the search from 2. We put a 0 here. Then we go to 0. So notice that 2 has not been, let's just put something else here to connect these two. 2 has not been, even if there's not an edge here, it doesn't really matter. So what you do here is your 2 is not being done yet. So you put a thing here 0 and then you move to 0. This. And you put a 1 here. The pre number is 1 because you visited and you put a number here. And then from 0 you visit to 5, you put a number here, 5. 2. Then from there you can't move further. So you just move back from here, right? So this vertex, that means has been explored. So you put a post counter here 3. I hope you people are able to understand this thing. How we write the 3 here. Because it doesn't have anything else to visit from here. So the search ends here. This has been explored, so we end it. This closes the counter for 5. And then we go back to 0 and we see that there is other vertex to explore, which is 4. We go to 4 then. And then we continue the counter from 3, which is 4. And then from 4, we visit 3. And at 3, we put a counter 5. 3 counter 5. And then from 3, there's nowhere to go. So this has been explored. So we put a 6 counter here, and then we go back to 4. This is the last one. This was the last entry, so we go back to this one. So 6, and you write a 7 here, the post counter, because from 4 there is nothing to explore, nothing more. If there was another edge here, then you write this thing here. But since we do not have anything from 4, so 4 is also explored. We close the counter here for 4, 7, and then we come back to 0 and see 5 and 4, only 2 things are there, and they both have been visited. So we close the counter here as well. And then we close the counter here. This counter, keeping the counter thing clear. Is this clear to everyone?
But ma'am, one doubt, ma'am. But from 3 to 5, there is a one counter, right?
3 to 5, but 5 has been explored, right? You can't. We've already discussed this when you are discussing. This is a DFS tree, and before anything, it's a tree. So you can't have an edge from 3 to 5.
Okay, we are discussing a tree. Okay, ma'am. Okay.
It's a tree.
Just get confused, ma'am, with
Okay,
all
that's
the
all
things.
right. So this thing is here, and then you look at this one. So it's obvious that this is not a part of this tree. So that means everything here cannot be explored from any vertex here. So it can't be explored from 2. That's why it's not a part of this tree. And then you have this thing. And then you start from, let's say, 1. You start your search from 1. Don't start from 1. There's nothing there. Let's just start from 7. So you keep a 7 here. And then we resume the counter from here. You ended at 9. So you keep a 10 here. This is when you visit. This is when you visit the vertex. This is when you're done exploring the vertex. So we keep a initial counter. The pre-counter is 10 here. And then we move to 6. And the counter is 11 here. Pre-counter. And then we move to 1. The counter is 12 here. And then from 1, there is nothing to explore, nothing to visit. So 1 is explored. That means it's 13 here. Then you come back to 6. And there is nothing more to visit. So this is also explored. 14 here. And then you come back to 7, nothing more to visit. So it's 15 here. Is this thing fine? So this is how you keep a counter.
Yes, ma'am. Ma'am,
this counter? Yes.
Ma'am, do we need the counter in breadth first search also?
No, because we don't keep a counter there. Because in a breadth first search, you complete. In a breadth first search, what you do is you just keep doing everything together simultaneously. It's like you're doing the tasks together that are on the same level. So you don't need a counter. There are levels there. That's why there are levels. That all of them are on the same level.
Yeah.
But here you need a counter. So why are we numbering? Why are we keeping a counter here? So this is to discuss the non-tree edges. Let's just come to our original thing, non-tree edges. Non-tree edges, there are 3 types of non-tree edges. One is the forward edge. So one are the edges that you see in this tree. So all of these, this was the original graph. This was the original graph, and this is the tree for it, right? So these all, this 0 to 2, 1 is a tree edge. So you can't tell it from here. If you just look at this thing, you can't tell which one is a tree edge. Or maybe you can still identify, but you can't exactly tell which is. So for that, you need to draw a tree and then see which edges are part of the tree. And then you can tell if it's a tree edge or not. And then there are non-tree edges which are not a part of this tree, but there are still edges here, right? For example, there is an edge from 7 to 1, but there is no edge from 7 to 1 here. That's a non-tree edge because it's not part of the tree. So there are 3 types of non-tree edges. One is the forward edge. Then the other one is back edge. and then there is a cross edge. So that's we're defining it here. What these three edges are. Forward edges, let's just have a look at this. Let's just have a look at the counters. So if we look at this thing, 0 to, what are the edges that are missing here? Let's just mark the three edges first. 0 2 is a tree edge. Then 0 4 is a tree edge. 0 5 is also a tree edge. 4 3 is also a tree edge. But 3 and 5 is not a tree edge. Right? That means it's a non-tree edge. So let's just look at this one, 5 and 3. So we say if we formally define it, it is this. UV is a forward edge if you're pre-U and post-U. I hope you know what pre-U and post-U thing is. It's this. The initial counter number that we were calling here. This thing. This number is the pre-U and this number is the post-U. This is, if this thing is contained in pre-V, post-V, then we say it's a forward edge. And if it's the other way around, we call it a back edge. Let's just see an example. Let's just see through an example which is the back edge and which is the forward edge. It's the opposite here. So if UV is a back edge, if pre-V, this is V, post-V is contained in pre-U, post-U. These are the formal definitions of non-tree edges. And let's just try to see what is 3 to 5. Which one is, this is definitely not a tree edge because there's no edge here. So it's a non-tree edge. Let's just classify which one it is. So let's just see the counter at 2 and the counter here is 2. The pre number for 5 is, there's an edge from 3 to 5. So we want to check what is 3, 5. So let's just see the pre number of 3 and post number of 3. So pre number of 3 is 5. Post number of 3 is 6. And then, no, this is for 3, right? And then for 5, you have 2 and 3. So we see that 2 and 3 is, this 2 and 3 part is contained in this thing. That means this is contained in this. That means if there was an edge from 5 to 3, then it would be a, wait, according to the definition, it's PV. If there's an edge from 5, where is the edge from? The edge is from 3 to 5.
3 to 5.
Okay. The edge is from 3 to 5. Let's just see which is contained in. So we know that 5 and 3, 5 is contained in 3. So
I'm not
that
clear
means
how
it's
you're saying 5 is contained in 3. What does that mean?
not 5 contained in 3. I mean this interval is contained in this one. This is just for you to see that this is for 5. This is the pre-counter, post-counter number for 5, and this is the pre-counter, post-counter number for 3.
Yes, ma'am. Numbers are okay, but ma'am, how you are relating 2, 3 with 5, 6?
3 is considered an interval here. What we do here is we see, here we look at it, and then we see 2, 3. So what happens here is, if you have 2, 3 for 5, and you have 5, 6 for 3. So what does this actually mean? If we look at the tree, this means that you visited this 5 first, then you moved along, and then you visited 3, right?
Yes.
And then you got done with, okay, this should be a cross edge then. Wait. Let's just define cross edge too, and then we'll see which is what. because it could be a cross edge too. But wait, if there is an edge from here to here, and they have the sharing counters, 2, 3 is the 2, 3 is not contained in 5, 6, right? And none of it is. This is 2, 3, 5, 6, right? So these are disjoint. Sorry, I made a mistake here. They are disjoint. So that means it's none of these. So it's neither a forward edge nor a back edge. That means it's the third one. So we'll define the third one here. It's the cross edge. And the cross edge is if pre-V post V and intersected with pre-U post U. And if this turns out to be empty, then it's a cross edge. That means if they don't have, so if you see something like if the initial counter is say 2, 3, like in this one and 5, 6 in this, the other one. So 2, 3 is here, 5, 6 is here, and they are disjoint. That means it's a cross edge. So this one that you see here is a cross edge. This is a cross edge. Is this fine?
Yes.
And then we'll see if there is an example of back edge or not, back and forward edge. So if you look at this thing, okay, I forgot to mention the arrows here. Now I don't even remember the arrows. It's the correct order. Yeah. So if you look at 7 and 1, so 7, 1 is not a 3 edge. Let's just see what is 7, 1. What you see here is look at the counter here. It's 10, 15 and it's 12, 13. So 12, 13 is contained in 10. Wait, is it? It is, right? It's the other way.
It's just overlapping.
13 is not overlapping. It's 10
Okay,
is
okay.
here,
Yes, ma'am.
15 is here, 12
Yes,
is here,
ma'am.
13 is here. So they are contained, right? That means it's
Yes.
a forward edge. So this one is a forward edge. So you don't draw it here because it's a tree. You can't have a cycle in tree. But here, if you look at this one, this is a forward edge. And I don't think we have a back edge in this one. So back edge is when it's the other way around. So it would look like this. In a graph, it would look like this. Let's just say if you have this thing. So we know that these two, and then the closing one is this thing. Do I need to do one example for back edge too? I'm just giving you another fact that's there for forward edge and back edges. Back edges, what they do is they form cycles. So this one, if these are parts of the tree, then this is going to be, can you tell which edge is this? It's not a part of the tree, obviously. Which edge is this?
Forward edge.
Back edge, ma'am.
And we even figure out if from just this thing. So if we look at this thing, we first need to know where we start the search from. So if you start from here, you keep a counter here, 0, and then you go to this one, keep a counter here, 1, and then close the counter here, 2. And then from here, and then start from here, the counter will close here, 2, 3. And then this is something totally different from these two. So you'll have a 4, and so it depends on what you're taking. But and now if you start from here, so that's what we're doing. Let's just start from the other one. This was it, right? Let's just start from this one. You'll put a 0 here, and then a 1 here. It closes here, a 3 here. Not a 3 here because we're not done exploring it yet. So we'll put a 3 here. So you do understand why we're not putting a 3 on this one. We're not closing the counter for this edge. For this vertex, this one. because it is not explored yet. There is still something connected. There's still an edge from here. So there's 3 here. Then this is being explored. So there's a 4 here. And then you have a 5 here. This thing it is. So if you look at this thing, if you make a tree, you will have this thing 0. And then from 0, you'll have 1 and 4. This is 3. Let's just call this A. Let's just call this B. And let's just call this C. 0 and putting numbers is confusing. A, and then you have a C, and then you have a B here, right? With counters 0, 5, 1, 2, and 3, 4. So if you look at this, again, this is not this is again an example of cross edge. This is not a four. What happens in a back edges, I'm not able to figure out an example right now. But it's just totally the opposite one. So it looks like this. You go from here, and then this is considered if this is what happens in a forward edge is the cycle is not completed. So it's like this. So if you see a forward edge of 3 edges, then this is not a cycle. But if it's a backward edge, it forms a cycle. A backward edge is going to form a cycle like this. So instead, we have a forward edge here, right? It will reverse the direction of this edge. So if we'll make it from here, look at this. This is stopping it from completing the cycle. This were to be a cycle if the direction was this. So if you take the opposite direction, instead of 7 to 1, if you take 1 to 7, this will become a back edge. Is it okay? Because then this interval would be contained in this. I hope that's clear. Do I need to write it down or is it clear? What I'm trying to say is that in this case, where the example that we did this one, 7, 1, and it was the last vertex, 6. And the edges, I guess, were from here, and then we have an edge here, which is this edge essentially is stopping this thing from becoming a cycle. If instead it was this thing, you will have a cycle here. And then this would be a back edge, because now what you're doing is your counter for 1, this is a forward edge because your counter for 1 is contained in the counter for 7. The pre-number for 1, pre-number for post number for 1 is contained in pre-number for 7 and post number for 7. This interval it is contained in. That's why it was a forward edge. But if you will take the edge from here to here, now you will have the opposite thing, right? This will be a back edge. I need to know if it's clear or not. Otherwise, we'll discuss it in more detail.
Ma'am, please discuss this in detail.
Ma'am, backward edge will make it a complete cycle, and the forward
How
edge will not
sometimes
make it a cycle.
yes, that's if there are only 3 vertices, that's how you identify if it's a back edge or it's a forward. It's a quick way to see if it's a forward edge or a back edge. If instead of this thing, in this case, you can see you have an edge from 7 to 1, right? And if you want it to be a forward edge, for a forward edge, the condition is the pre-number post number for this should be contained in the pre-number post number of this, which is being satisfied here. That's why it's a forward edge. But if instead you have an edge from 1 to 7, then it becomes the opposite, right? Because then you will have.
Ma'am, how it will be possible? This is contra, it can be one at a time.
I can't hear you.
Can I, ma'am, again, can I ask?
Yes.
Ma'am, you are saying about the condition if 7 to 1 is the pre-comma may
Okay, let's just
pause.
assume you've already made.
It
Give me a second. You've already done it for this one. Let's just assume that instead of an edge from 7 to 1, we have an edge from 1 to 7. Okay. And now we are, so this won't change. Do you agree that this part is not going to change? Only this is going to change, right? This will change if we change the edge here. So we're changing only this part. This is the original graph. We're changing it from this to 7, 6, and 1 here. So we're taking it this. This time we're taking it to be this. Is this okay? We're discussing the doubt here. Someone had a doubt in this one. Please say something if you understand what we're doing. We start, so the counter starts from 10 only here. You had a 10 here. So the initial counter, the pre-counter for 7 still is 10 because you ended with 9 here. So you start from 10 here. Because this part we didn't make any change to this. We start with a 10 here. Then we go to 6. So we keep it 7, 11 here. And then we move to 1. Because it's a depth first search. That's why we are going this way. So the counter now becomes 12. So it's still the same thing. So the numbers haven't changed. Do you understand this part?
Yes, ma'am.
Even if this thing was there, even if you change it a bit, this is still valid. So for this one, it's still this tree. And this one, it's still this tree. Nothing changes. So what happens is you just need to make sure. So the edges, original edge, in this one, the edge is from 7 to 1, 7 to 1. So what you're doing is this okay, even if you look at it, no, it will look like a forward edge because it's going in the forward direction. But that's not the right way to identify. It's a hunch that you can use to identify this thing that this is going in the forward direction. That's why it's a forward edge. But what you do is by a forward edge, you mean that you visited this thing first and then you move to this one. That's what a forward edge means. So if there's an edge from 7 to 1, that means that this counter began first. So this thing began first. This thing began later, and this ended first, and this ended later. So that means this exploration, the exploration of 1 is a part of exploration of 7. Do you understand now? That's why it's a forward edge. The exploration of 1, what does 12 and 13 tell you? It tells that it starts from 12 and ends at 13. The exploration is ended at 13. And here the exploration ends at 15. So the exploration of 1 is a part of exploration of 7. That's why there's a forward edge. So we call it a forward edge. But in this case, what you do is, now, if this is the thing, I think we've messed up the counters here. Because you have 10, then you go to 6.
Excuse me, ma'am.
Yes.
The last thing, can you please just once, the last you said about
This
the
one?
counters. Yes, ma'am, yes.
Okay, what we're saying here is that if you have forward edge basically means that it's in the forward, this one is the ancestor and this one came later. That's what it means. Forward edge means this. So if there's an edge from 7 to 1, it should, in the tree also, 7 should be, the exploration of 1 should be a part of, do you understand what exploration is? Exploration means first visiting the vertex and then getting done with it, visiting every neighbor of it. So you visited 1 at 12 and then you visited every neighbor of 1 at 13. But you started with 7 at 10 and you ended with exploring 7 at 15. That means this thing is a forward part. This is an ancestor of this. You just need to know the definition. You don't need to get into the detail. You just need to know that if this interval is smaller, this interval is contained in this interval, then this edge, direction matters, then this edge is going to be a forward edge. And if You have an edge from here to here, from 1 to 7. Now what happens is you have an edge from 1 to 7. If you consider this thing, the other one, that we've changed this edge, then this will be this thing, right? Now this is the backward edge. Why? Because this interval is contained in this one. It's just the definition of forward edge and backward edge. You don't even need to get into the depth of why we call it a forward edge, why we call it a back edge. Just remember the definition. That the vertex that you visit later, if this is contained, this is the interval. It's not a formal term for it, but let's just call it the interval here. If the interval for this vertex, which is visited later, is contained in, if it contains this one, of the one where you started. So you start from here, you end here. This is 7, this is 1. So if the interval of this one is contained in the interval of this one, then it's a back edge. It's
Okay,
fine.
ma'am. Yes, ma'am.
Okay. So that did not change the counters, only the direction has changed. That's why previously we were considering 12, 13 contained in 10, 15, because previously the direction was from 7 to this. So okay, let me just simplify things for you. If you have it from 7 to 1, you want the interval of 7 to contain the interval of 1 for it to be a forward edge. So from where you start, you want the interval of that point to contain the interval where you end. Is that fine?
Yes, ma'am. Ma'am, actually, this is new to me, na. That's why in a forward edge and backward edge, it will take me some time. That's why I'm asking again and again.
That's
Nothing
all.
else.
Okay, so just if in case, that's why there are definitions written here. If in case you can't understand things from there, just use the definitions. They are the easiest.
Ma'am, understood all the topics.
Okay, so this part when you consider so this is a feature of forward edge and back edges. So when you consider forward edge, it does not form a cycle. In fact, it stops from a cycle being formed, like this one. This is stopping this to be a cycle. No, not this one, this one. This edge is stopping this thing to become a cycle. So this is a forward edge. But it's always the best way to figure out if it's a forward edge, back edge, or cross edge is to keep a counter. That's the formal definition of it. This is just a way to identify if it's a forward edge or back edge. Is it fine?
Yes, ma'am.
Okay, and then we have, so there's a term called strongly connected and connected. So when we talk about connected, we talk it in the sense of
Ma'am, can we
undirected
take
graphs.
topic tomorrow?
Okay. Shall we continue the left part tomorrow?
How many percentage you have completed today?
There's still left. So
Still like
okay,
40%.
It's been yeah, it's been more than 50%. So we'll just do it, and it's been 3 hours now. So let's do the rest tomorrow then.
Yes, ma'am. Tomorrow.
Sure, ma'am.
And there are
Yes.
still 50% more.
No, it's not 50%. It's just a tiny bit. I think we'll get done with it in an hour or something.
In a hour.
Yeah, 1 hour.
Yes,
if you take.
resting tomorrow.
But
Okay.
tomorrow what time we have session? Because we don't have math session tomorrow.
We don't have one yet, so we'll have to schedule one for it.
Or could you
For Sunday.
schedule it same time from 8?
Yeah, if there would be a session, it will be from 8 only.
Okay, thank you so much.
Okay.
Ma'am, tomorrow there is no max session. There is
I
an
know.
empty.
We'll have to. I'll have to check for it because we're not done with the summary. Else we'll do it some other day.
Yes, ma'am.
That's the most I can do, or I can continue with the session now. But
Ma'am, I think let's finish today itself.
Already 3 hours.
Ma'am, it's already very late, ma'am. It's going to be
Half
11.
past
Ma'am, okay, yes, everyone, what everyone says to it's late only, but if we complete today itself, it will be because we can revise on tomorrow. Then it will be good. It will be easier for us. For us.
Okay, okay. We'll
If we
discuss
take
it
on to
tomorrow.
tomorrow,
Just revise everything that's been done in the class. We'll discuss everything else tomorrow. Okay.
Thank you.
okay, ma'am.
Thank
Yeah,
you,
ma'am.
everyone.
Thank you.
Bye.
Thank you, ma'am. Bye,
Thank you,
ma'am. Good
ma'am.
night, ma'am.
Hello.